Okay, guys, great. So let's just review what we did, and then I want to make a few comments. I'm not going to comment on the problems for this chapter. In fact, I think that they were all pretty straightforward, and we covered everything that you needed to cover in class to complete the problems. Okay, so this chapter has been all about computing Feynman diagrams. As I said, this chapter is all about tricks to compute integrals. So we started off studying a specific example, but the lessons that we learned are completely general. So you write down your Feynman diagram, you know how to do that, and you'll get some integral that you have to perform. In this integral, it'll be an integral over momentum, and then you'll have 1 over some product of denominators. The first thing that you will do is you'll use Feynman's trick to write the product of denominators as a sum of denominators, and then you'll complete the square. So this is always the first step that you will perform. If you've got a single denominator, you don't need any Feynman parameters. If you've got a product of 2 denominators, you need 1 Feynman parameter. If you've got a product of n denominators, you need n minus 1 Feynman parameters. The Feynman parameter here is x, and the Feynman parameter integrals always go over a finite range from 0 to 1 if you've only got 1, and if you've got a few, well, it's some nested integrals, but they all start at the lowest value of 0 and end at the largest value of 1. So it's always integrals over some finite interval. Then when we've got this expression for our Feynman diagram, typically it's divergent. So we have to regularize it somehow. We're using dimensional regularization. So that means we go to d dimensions. So this is the dimensional regularization step. We now have an integral to do over d dimensions. How do we do that? We look it up in a table, okay? And we used formula A dot 44 of Peskin and Schroeder with n is equal to 2, or alternatively, look in chapter 21 of the notes, and all of the formulas are there. We then want to remove the regulator. To remove the regulator, we go back to 4 dimensions. 2 useful formulas to remember here are that 2 minus d over 2 is equal to epsilon over 2, and we want to take epsilon to 0, or at least very small, and d over 2 is 2 minus epsilon over 2. So plugging this into that formula and using the expansions for the gamma function and for something raised to the power of epsilon, we got this result over here. And so finally, this is the answer that we got for the Feynman diagram. We have one integral left to do. It's an integral from 0 to 1 dx. So we can easily do this integral numerically if we wanted to. Notice that 2 over epsilon term is actually divergent. If you were to send epsilon to 0, you get infinity. And that's the meaning of the fact that this Feynman diagram is divergent. But of course, we can work for epsilon small, but not quite 0, solve our matching conditions, so actually renormalize the theory. And then once we've done that, take epsilon to 0, and the infinities won't bother us at all. Good. Now there's a comment. There's one loose end to tie up. If we look at that log sitting there, it might look a little bit weird to you. It should look a little bit weird. So let's think about this log. Well, we can rewrite this log as follows. This is the log of a over b is log a minus log b. So this is log of 4 pi. That looks fine. But then we've got minus the log of m squared plus p1 plus p2 squared times by x and x minus 1. Now, this looks distinctly weird. It has the dimensions of mass squared, so it's not dimensionless. But you cannot take the log of a dimensionful number. You can only take the log of something that is dimensionless. And that means you need to now introduce a new scale, mu squared. So mu squared must be introduced so that the argument of the log is dimensionless, okay? So dimensional regularization forces you to introduce a new scale. We said that dimensional regularization had to break something. If you had a scale invariance theory, it would break scale symmetry, but at very least, it forces you to introduce a new scale. And that's a side effect of dimensional regularization. But actually, it's the best we can do. This scale that we've introduced is actually physical. So mu is physical. And let me tell you what I mean by that. If you study things like, let's say you study the electric charge squared. So let me write this as E squared. In fact, you might say, well, the electric charge is 1.6 times 10 to the negative 19 coulombs. That's not true in quantum field theory anymore. In fact, the charge starts to depend on the energy scale. And a dependence on the energy scale here means a dependence on this new scale, mu. And the way the electric charge behaves at very low energies, it's small, but as you get to higher and higher energies, it gets bigger and bigger. So this is how the electric charge behaves. It doesn't always have to behave like that for other theories, like, for example, for QCD, okay? So this would be for something like quantum electrodynamics. If you were studying quantum chromodynamics, the quantum field theory for the strong charge, then we have a coupling, the QCD coupling, and what you find is at low energies, it's very big, but it becomes very small at high energies. This fact that the coupling constant becomes small at very high energies is called asymptotic freedom. And this, in fact, won a Nobel Prize for Gross, Wilczek, and Politzer. The discovery that at high energies, the coupling constant of quantum chromodynamics actually goes to zero. The theory actually becomes very weakly coupled. And all of this is encoded in the appearance of this new scale mu. And in fact, what we will do in chapter 24, we are going to calculate how the charges change as the energy scale is changed. We say how the charges run. And the function which describes how the couplings run as you change the energy scale is called the beta function. And we'll see how to calculate beta functions. And once we've calculated them, we'll see how to determine the running of the coupling constants. But now that we can actually evaluate Feynman diagrams, we can return to our matching conditions and perform the one loop renormalization of our theory. And that's what we're going to do in the next chapter.